Hi, this is a demo presentation of our paper, DOF-GS, Adjustable Depth of Field 3D Gaussian Splatting for Post-Capture Refocusing, Defocus Rendering, and Blur Removal. Given multi-view defocused images with defocus blur, DOF-GS is able to reconstruct a sharp 3D scene represented with 3D Gaussian points, which can function as tools for novel view synthesis, with inherent support for controllable rendering of depth of field effects. In recent years, 3D-GS has enabled high-quality 3D reconstruction from multi-view images and fast novel view rendering. However, 3D-GS is built on a pinhole camera assumption. That is, it assumes all input images have a large depth of field where everything appears sharp. But in real-world scenarios, cameras often follow a thin lens model with a finite aperture. This leads to depth of field effects, where out-of-focus regions appear blurred. The pinhole camera assumption introduces several limitations. First, it prevents the method from controlling depth of field effects in rendered images. Second, it cannot effectively handle defocus blur in input views, leading to blurry reconstructions and multi-view inconsistencies. With this motivation, we propose DOF-GS by extending vanilla 3D-GS with several key components. At its core is a differentiable COC-guided DOF renderer for efficient defocus modeling. We also learn 2 camera parameters per view to fit defocus and apply a detail enhancement strategy for all-in-focus rendering. This is our overall pipeline. It starts from estimated point clouds and poses from a structure from motion method and reconstructs a 3D scene from multi-view defocused images. Next, we introduce the core, the differentiable DOF rendering process and camera model. We use an approximate thin lens camera model with 2 learnable parameters, aperture size Q and focal distance F, which defines the depth of the focal plane. The circle of confusion measures the blur size when a 3D point is off the focal plane. Its radius is computed by this formula, where 0 is the object point's depth. Now let's look at the differentiable DOF rendering process. As in 3D-GS, 3D Gaussians are projected onto the image plane to form 2D Gaussians. Using the thin lens model, we compute COC radius to build blur kernels for each 2D Gaussian. The 2D Gaussians are then convolved with their corresponding blur kernels, resulting in blurred Gaussians. Finally, the image is rendered by compositing the blurred Gaussians. We also render a COC map by compositing the COC radius values according to blurred Gaussians. Over iterations, it quickly aligns with the blur distribution in training images. Now we introduce the detail enhancement strategy for all-in-focus rendering. The key idea is to leverage in-focus regions in training views to directly supervise the rendered AIF image. To achieve this, we use a lightweight network to predict in-focus masks from defocus inputs. These masks help the model learn sharp content in the AIF renderings. All components are trained jointly using reconstruction and regularization losses. Please refer to our paper for more details. Here is an analysis of the optimized focal distances across training views. They closely align with manually labeled focus ranges. As shown in the sampled views, the optimized focal distances align well with the focus cues in the images. Now we demonstrate controllable depth of field rendering from the reconstructed scene. As aperture increases, blur in out-of-focus regions becomes stronger, and changing the focal plane controls which region stays sharp. We also evaluate our method on all-in-focus novel view synthesis. Here are quantitative results. Our method achieves competitive results compared to state-of-the-art deblurring nerve and 3D-GS baselines, demonstrating its effectiveness in producing sharp novel views. Moreover, thanks to our unique DOF rendering module, our pipeline is significantly more memory efficient than bags when handling high-resolution inputs. Here we show visual results for all-in-focus novel view synthesis. Our method effectively recovers fine details in challenging regions like text, fruit stacks, and wall textures. These 2 video demos showcase our method's capabilities. Each video demonstrates both novel view synthesis and controllable depth of field rendering through post-capture adjustment of focal distance and aperture. To summarize, in this work, we propose DOF-GS, a framework that uniquely enables post-capture refocusing and reconstructs sharp 3D scenes from multi-view defocused images. At its core is a differentiable and efficient DOF rendering module based on a finite aperture camera model. Feel free to check out more information on our project page. Thank you for watching.